Okay, so welcome back to the next talk that we have. The next talk is given by Yoshitsugu Takei from Doshisha University. So Yoshi, we first met probably in Cambridge in 1995. So Yoshi is one of the old guard, should we say now. So Yoshi has been working on formally exact WKB and Painlev for some time. The research group at RIMS in Kyoto now, Yoshi has moved to Doshisha University, is one of the most well-known in the area. And I'm very pleased that Yoshi is able to be here, and hopefully we're ready to hear his talk on two-parameter instanton-type solutions of the Painlev equation and their analytic interpretation. So,
thank you. So thank you very much for the very kind invitation. So as Chris explained, I was a participant with a program expression asymptotics held here in Cambridge in 1995. So I'm very happy to be here again, in Cambridge, and as such a person, perhaps, according to the classification of Chris, I'm belonging to the first generation or asymptotics. I'm not sure, but anyway, as such a person, I would like to today I would like to give a review of the exact Wkv theory for Painlev equations developed by Aoki, Kawai, and myself since 1990s. And so perhaps the most of my talk will be devoted to the very old results. I'm sorry, but maybe the last part of the talk I will discuss some recent my recent trials as well. So let me start here. And first, I would like to show the list of the Painlev equations. So perhaps, as you know, Painlev equations now are very important objects, both in mathematics and physics. And usually, Painlev equations are classified into 6 groups. But sometimes they are more recently, the third Painlev equation. This one, the third Painlev equation is classified to 3 subclasses like this. Oh, sorry. To 3 subclasses like this. And hence, usually, more recently, Painlev equations are classified into 8 groups. Anyway, and to discuss the exact Wkv theory for such nonlinear, second-order nonlinear differential equations, we have introduced a large parameter, eta, like this here. Eta is a large parameter. Basically, this is the inverse of the Planck's constant, physically speaking. And we want to develop some WKB analysis for such nonlinear differential equations. This is our main purpose of this research. And in fact, for example, the 6th Painlev equation has a very complicated form of the equation. But anyway, all of the equations have this form. That is, all of the equation has this form. That is, the second derivative of unknown functions is given by this right-hand side. And so large parameter is introduced here, just here. So the coefficient of the large parameter contains only the unknown function lambda and the independent variable t, like this. And originally, this equation, and if you put eta is equal to 1, then we obtain the original Painlev equations without a large parameter. And these equations were first discovered by Painlev and his student Gambier at the beginning of the 20th century. And according to their discovery, the most basic property of this equation is the Painlev property. That is the meromorphy of the solution of this nonlinear equation. Or in other words, all the movable singular points are poles for every solution of this equation. And also, almost at the same time, it was discovered by Fuchs that this nonlinear equation has a close relationship with the so-called isomorphous deformation theory of some linear equations, like this. And very roughly speaking, a large parameter eta is introduced in this nonlinear equations, so that this associated linear equation becomes a Schrödinger equation like this. So here, eta is a inverse of the Planck's constant. So this is the usual form of the Schrödinger equation like this. And this relationship, after that, this relationship is extended to all of Painlev equations by Jimbo, Miwa, and Ueno, around 1980s. And in this analysis, this relationship plays a crucially important role. And our main interest lies in the asymptotic analysis of these nonlinear equations. But there are many asymptotic studies for these equations. The first study was done by Boutreau, as it's well known. And after that, there are many works done by Russian people like Itz, Kapaev, Kitaev, and so on. And also, Joshi, Narini, doing a very important contribution to the asymptotic analysis. And also, Kostin et al. Doing some similar kind of asymptotic analysis. And more recently, these people, Aniceto, Schiappa, and Funk, considering some series or some resurgent analysis of these nonlinear equations from the viewpoint of quantum Fourier theory. But here, I would like to review the exact Wkv theory developed by Aoki, Kawai, and myself. So let me start with the explanation of our theory. So very roughly speaking, we want to construct a Wkv theory for such nonlinear equations in parallel to the case of linear equations, that is in the case of Schrödinger, second order Schrödinger equations. And for that purpose, we need some formal solutions which correspond in a sense of Wkv solution of linear Schrödinger equations. And in fact, a large parameter is already introduced into the nonlinear equation like this. And we can easily construct this kind of formal solution, that is a formal solution of the formal power series in the inverse of the eta, that is in the power of Planck's constant. So, and in fact, this kind of formal solution is very easily constructed. We have just to substitute this expansion into the equation. Then we can easily find that this top order part, lambda 0, should satisfy this algebraic equation. And the higher order terms, lambda 2 and lambda 4 and so on, are recursively determined. But this formal solution does not contain any free parameter. So to discuss general solutions of this nonlinear equation, we also consider trans-series solution. That is, we start from formal power series solution, and we add some exponential small term to this formal power series solution like this. And it is easily seen that this subleading part should satisfy the linearized equation of Painlev equations around this formal power series solution like this. And we denote this linearized equation of Painlev equations by delta Pj here. Delta Pj here. So we pick up an exponential small solution of this linear equation, and we add such as perturbation to the formal power series solution. And also we add some higher order corrections, then we can construct such a formal solution, trans-series solution with one free parameter. But more important in this talk is the instanton-type solution. In fact, this is the solution with two free parameters of this form. So basically start with this formal power series solution, and we consider the general solution of this linearized equation, and we add a general solution to this linearized equation to this formal power series solution, and we construct formal solution of the nonlinear equation. This is an instanton-type solution of Painlev equations. And this is the main player in our Wkv approach here to this nonlinear Painlev equation. And this is a very brief description of the construction of such instanton-type solution. So the easiest way is to brute force extension of the construction of one parameter trans-series solution. That is, formally we consider general solution of this linearized equation at a formal power series solution of Painlev then we consider the higher order corrections. Then we can construct such kind of formal solution in a brute force way. This is the most easiest way to construct such a solution. But more efficient way is to use employment of the multiple scale analysis. This is first done by Aoki, Kawai, and myself for the second order Painlev equations, and also extended to higher order Painlev equations by Aoki, Honda, Umeta, and so on. But in a sense, more useful construction of such formal power series, such instanton-type solution is the use of the Bark formal form theory. So for this construction of the formal solution, I will explain later. This is, in a sense, more efficient and more useful way of construction. And so this is a construction of instanton-type solution. But the main purpose of our study is to analyze the Stokes phenomenon for such formal solutions of nonlinear equations. And in that sense, instanton-type solution or two-parameter translated solutions play a very crucially important role in describing such a Stokes phenomenon for Painlev equations. And just like the case of linear equations, such Stokes phenomena is expected to occur on the so-called Stokes curve, that is Stokes curve. And in the case of Painlev equations, such a Stokes curve and also turning point is defined by this definition. That is, we define the Stokes geometry of the Painlev equation, that is turning point and Stokes curve of Painlev equations, just as a Stokes curve and turning point of linearized equation of Painlev. So in fact, linearized equation is just linear Schrödinger equation in a sense. So we have already known that what is the turning point and Stokes curve for this linear equation. And we extend such a notion to nonlinear equation by using this linearized equation. And hence, in this case, turning point becomes the zero of the leading part of the potential, that is the derivative of the coefficient of the eta square part with respect to lambda like this. And also Stokes curve is defined by this formula, because in this case, linearized equation is given by this formula. So we show some examples of the Stokes geometry here. So the simplest case, that is the first Painlev equations case. So in this case, the F1 function becomes a quadratic polynomial in lambda like this. And the linearized equation here becomes this one. So I have missed delta here. Okay, this is anyway, this is the Painlev equation. Anyway, and hence in this case, we have there exists just one turning point at the origin like this here. And 5 Stokes lines or 5 Stokes curves emanate from this unique turning point at the origin. But precisely speaking, such a Stokes geometry or Stokes curves are defined by this top order part of the formal power series solution lambda 0. Then that is, we should consider this geometry on the Riemann surface of this lambda 0. And hence, this is the picture in the original T-plane, but we should consider this picture on the Riemann surface of lambda 0. And in the case of P1, such a Riemann surface, the global coordinate of such Riemann surface is given by the lambda 0 itself. And we can write this picture on the lambda 0 plane as well. And hence, on the lambda 0 plane, we have a similar kind of picture like this. Again, we have only one turning point at 0 and 5 Stokes curves emanate from here, from this turning point. This is the picture for the P1, and one more. This is the picture for P2. In the case of P2, F2 is a cubic polynomial, and hence its derivative is just a quadratic polynomial like this. And lambda 0 should satisfy this cubic polynomial. And hence, the Riemann surface is 3-sheeted. And in this case, we have 3 turning points, and the Stokes curve should be written on the Riemann surface of this cubic equation like this. So this is the picture on the first sheet, and this is the picture on the second sheet, and this is the picture on the third sheet. And this weakly line indicates a cut. This cut is a cut connecting the first sheet and the second sheet, and this cut is a cut connecting second sheet and third sheet. And there are 3 turning points here like this, okay? And from each turning point, there are 5 Stokes curves emanate. And solid line here indicates that this Stokes curve really exists on this sheet. And this dotted line indicates that this part is not on this sheet, but on this sheet, for example. So in this way, the picture of the Stokes geometry of Painlev equation should be written on this Riemann surface. And in the case of P2, yeah, again, we can take this lambda 0 itself as a global coordinate of the Riemann surface. Then if we write the picture on the lambda 0 plane, then it's a more, in a sense, simple way. Yeah, we can describe the Stokes geometry in a more simple way like this. So on the lambda 0 plane, we have again 3 turning points like this. And this origin corresponds to the point at the infinity on the third sheet. And also the point at the infinity in the lambda 0 plane, yeah, corresponds to the point at the infinity on the first sheet and second sheet. These 2 sheets are connected by this cut, and hence the point at the infinity consists just 1 point. So the point at the infinity on these 2 sheets, they correspond to the point at the infinity on this Riemann surface. So from these 3 turning points, yeah, 5 Stokes curves emanate, and they are all going to point at the infinity or to the origin. So this is a picture of the Stokes geometry of P2. And we expect some Stokes phenomena should occur on these Stokes curves for every Painlev equation. And to analyze such a Stokes phenomena, yeah, in this approach, there are 2 very fundamental theorems. And the first fundamental theorem is the local equivalence between the general Painlev equation Pj and the first Painlev equation. That is, we take a simple turning point T star of the general Painlev equation like this. So to distinguish 2 variables of general Pj and P1, yeah, we put tilde sign here for the variable for the of the general Painlev equation Pj. But anyway, we pick up a simple turning point T star tilde, yeah, of the J Painlev equation. Then we can prove that every instanton-type solution of Pj like this is transformed to some instanton-type solution of the first Painlev equation P1 by some pair of transformations like this. That is, as an instanton-type solution of the J Painlev equation lambda J tilde should be connected to a solution, to an instanton-type solution of the first Painlev equation by this formula. So this is a local equivalence. So here, T of T tilde eta describes the formal coordinate transformation of this form. And in this case, we are discussing the nonlinear equations. We also need a formal transformation of unknown functions. And this x of x tilde T tilde, yeah, describes such a formal transformation of unknown functions like this. So in this way, at every simple turning point of the general Painlev equations, yeah, we can reduce the equation to the first Painlev equation. So in that sense, the first Painlev equation can be a sort of as a canonical equation at a simple turning point. So very roughly speaking, this is a nonlinear analog for the transformation theory. Yeah, please. Yeah.
Thank you, Chris. You mentioned the keyword local in your explanation, but I wondered, in what sense could you say uniformity of the transformation? We're looking at a neighborhood of a turning point, but in principle, there will be poles, movable poles of the solutions. So what do you do with those?
In a sense, we have not discussed, such a uniformity yet, And in fact, this is just a formal transformation. So in that sense, it's a little bit difficult to discuss such a uniformity. So hence, we should, anyway, after that, at the end of this talk, I will return to that problem, In fact, this is related to some analytic interpretation of the transformation also, Anyway, this can be regarded as a nonlinear analog of the transformation of linear Schrödinger equations at a simple turning point to the AR equation. And in fact, in the discussion of the Schrödinger equations, the AR equation plays a crucially important role. In fact, in the matching process, we transform the general Schrödinger equation to the AR equation near simple turning point. And this is formal result, but it claims that such process is also possible for nonlinear Painlev equations. And this is a very brief explanation of the idea of the proof. In fact, to prove such a local equivalence, we make use of the isomorphous deformation theory. And in fact, that is, we should return to this. We should return to this. We consider this associated linear equation to construct such a local transformation of the unknown function of nonlinear equations. And in fact, we find that associated linear equation SLJ has always a double turning point at this point, lambda 0 tilde t. And at a simple turning point of the nonlinear equation, this double turning point of the linear equation merge with another simple turning point of the linear equation. And very roughly speaking, in this way, a double turning point lambda 0 tilde in that sense, and connected by a simple turning point near a turning point of the nonlinear equation, especially on the Stokes curve of the nonlinear equation like this. And very roughly speaking, we construct a semi-global transformation of the associated linear equation in a neighborhood of these two turning points, lambda 0 tilde and H tilde. And to obtain to construct such a semi-global transformation, not only the coordinate transformation, but also we need some transformation of the parameter. When we discuss the associated linear equation, t is just a parameter. T is an independent variable of the nonlinear equation, but t plays a role of the parameter. And to construct such a semi-global transformation, we need some assignment of the parameter as well. And by choosing some appropriate transformation, we construct such a semi-global transformation in a neighborhood of these two turning points. And in fact, we can prove that this transformation of parameter gives local coordinate transformation for the nonlinear equation. And the original coordinate transformation of the associated linear equation gives the transformation of the unknown function for the Painlev equation. And as a result, we obtain this kind of local equivalence of nonlinear equations. So this is the first fundamental result in this approach. And the second fundamental theorem is the connection formula for the first Painlev equation. In fact, the first Painlev equation can be regarded as a canonical equation at a simple turning point. And as I explained before, in the case of P1, there exists just one turning point at the origin, and 5 Stokes curves emanate from this unique turning point. And on each Stokes curve, we have the following types of connection formula. That is, if we consider an instanton-type solution in one sector, and we consider its analytic continuation across one Stokes curve like this, then because the Stokes phenomena occur on this Stokes curve, and corresponding parameter should be changed on each Stokes curve. And in fact, the connection formula for in the case of nonlinear Painlev equations should be a relation between these two pairs of parameters. And in the case of P1, we can give an explicit form of the relation of these parameters like this. This is the connection formula for the first Painlev equation. And in fact, again, to prove this connection formula for the first Painlev equation, we make use of the isomorphous deformation theory. In fact, we show this picture here. In fact, in this picture, now we are considering this Stokes curve, that is, this is in the T plane, so argument T equals minus pi over 5 like that. And in the lambda 0 plane, yeah, this is the picture in the lambda 0 plane. This corresponds to this Stokes curve. Argument lambda 0 is 2 pi over 5 or something like that. And as I explained before, on this Stokes curve, double turning point or simple turning point for the linear equation should be connected. But on each side of this Stokes curve, that is in this sector and in this sector, this connection is resolved in two ways like this. So the picture becomes different for the associated linear equation. And in view of this configuration of Stokes curves for the linear equation, we compute the so-called Stokes multipliers of the associated linear equation SL1. Then, because the configuration of Stokes curves are different between these two sectors, and hence the explicit form of the Stokes multipliers of the associated linear equations become different. But we obtain a such an explicit description of the Stokes multipliers by using the exact Wkv theory for linear equations. And if we, and in fact, the both-hand sides of this connection formula is nothing but the Stokes multipliers of the associated linear equation. And then the property that the Stokes multipliers of the associated linear equation around the point at the infinity are the first integrals of the first Painlev equation. This is the key property or key relationship between Painlev equations and monodromic deformation theory. So thanks to this key property, these two expressions should coincide. So this gives the connection formula for the first Painlev equation. So these two theorems are basically ingredient of this theory. And basically, combining these two theorems, we are expected to discuss every connection problem for the Painlev equations. So as a typical example here, I would like to discuss the most typical connection problem discussed by Abrovitz-Segoya, like for P2, like this. So Abrovitz-Segoya considered this the simplest second Painlev equation like this. And they considered a connection problem for this equation along the real axis. So they picked up a asymptotic solution near the point the plus infinity like this. So here they assume to be this constant is a little small constant. And because A is a small constant near Z equal plus infinity, the solution of this second Painlev equation is approximated by area function. So we pick up such a special solution with the asymptotics, just the same asymptotics with the area equation like this. Okay. And they considered analytic continuation of this particular solution with this asymptotics to the Z equal minus infinity along the real axis. And then they obtained that near the Z equal minus infinity, the solution should have the asymptotic expression described like this. So theta, they describe the phase transition, and also this square is some nonlinear correction term of the asymptotics. And in fact, they gave a very explicit formula describing this phase shift and nonlinear correction for this problem. This is the result. This is the most typical correction program for the Painlev equation. And in fact, such a connection problem can be discussed by our approach also. That is, this is the exact WKB approach. In fact, by simple scaling, this equation can be changed, can be transformed to this form. That is, this is the second Painlev equation with a large parameter here. And to discuss the Abrovich-Segars connection problem, we pick up a special solution, special instanton-type solution with starting the vanishing to leading part, lambda 0. In fact, this is a special second Painlev equation with 0 constant term, and hence, in this case, the aggregate part F2 0 should be factorized like this. So there are 3 choices for the top order part, lambda 0. And we pick up the vanishing lambda 0 like this. Sorry. Sorry, T is missing. Thank you. Here we need T, like this. That's right. And we pick up a special choice of the 0 for the leading part, lambda 0. Okay. And we studied this connection problem for the second Painlev equation first with non-zero C and take a limit C going to 0. And now then, if we consider the connection problem for the general second Painlev equation with non-zero constant C, then as I explained earlier, Stokes curves becomes like this. Stokes geometry should be written on the Riemann surface of this lambda 0, and there are 3 sheets. This is a 3-sheeted Riemann surface. And if we consider the limit C going to 0, then these 3 turning points merge to the origin. All 3 turning points merge to the origin. And the cut connecting these 2 simple turning points, disappears. And as a limit, the Riemann surface is decomposed into 2 connected components. In fact, this cut should survive, and hence the resulting Riemann surface is 2-sheeted part and 1-sheeted part. And we are considering the instanton-type solution of the of P2 with 0 constant time. We pick up the vanishing lambda 0. And hence, if we look at this factorization, we should consider this 3rd sheet for non-zero C. Then we consider the connection problem from +∞ to -3∞ along the real axis for non-zero C and take a limit. Then we should consider this problem on this 3rd sheet. Then the path of analytic continuation crosses 2 Stokes curves like this. So at each crossing point of Stokes curves, because these 2 Stokes curves are emanating from a simple turning point of the second Painlev equation, by our local transformation theory, we can expect that at each crossing point, a similar connection formula as P1 should hold. And hence, if we combine 2 connection formulas, essentially described by the connection formula for the first Painlev equation, then we should discuss the connection problem for such problem for the second Painlev equation along the real axis. And this is really the case. In fact, combination of 2 connection formulas for the first Painlev equation gives the second Abrovich-Segars connection formula for the for the second Painlev equation with 0 constant. So in this way, our exact WKB approach here is expected to solve any connection problem for any Painlev equation. But there is one very big difficulty in this approach. So in fact, in this approach, yeah, the instanton-type solution is the main player. But this instanton-type solution contains all instantons of this form. That is, yeah, in fact, as I explained before, yeah, phi j is this kind of integral, and instanton-type solution contains all exponentials. That is, all m, yeah, all integer m. And hence, instanton-type solutions contain exponentially large terms and small terms simultaneously. So analytically speaking, or mathematically speaking, it's a very big problem. In the usual asymptotic analysis, we cannot give an analytic meaning to this instanton-type solution. So hence, our fundamental theorem holds only formally. So to give a mathematically rigorous, yeah, proof to this fundamental theory, yeah, we need some analytical interpretation of such instanton-type solutions. So this is a very big difficulty in this approach. And such a difficulty is already pointed out by these people. So in what follows, yeah, we want to discuss analytical interpretation of this instanton-type solution. So this is the second part of this of my talk. Yeah. And to discuss the analytical interpretation of instanton-type solutions, we want to consider first, yeah, its prototype. That is the case of Wkv equation. Wkv equation is the first order nonlinear equation like this. So it is well known that this is equivalent to discuss the second order linear equation. But anyway, we discuss this kind of first order nonlinear equation first. And more or less, we want to extend some result to the Painlev equations later. So even in the case of Wkv equation, there is a similar problem of instanton-type solution, similar problem of divergence for the instanton-type solution. That is, in the case of Wkv equation, again, there is a large parameter here. We have two formal power series solutions, starting with this leading part, plus minus square root q. And we denote this two formal power series solution by this notation. Okay? And sometimes we decompose this two solution here is a sum of two odd part and even part. And starting with this formal power series solution, yeah, again, we can easily construct Torrance series solution or instanton-type solution with just one free parameter for this nonlinear equation. But according to the choice of this sign of square root, one of them is exponentially large. So in that sense, Torrance series solution or instanton-type solution of this Wkv equation again suffers from divergence problem due to the exponentially large term. And we want to discuss analytical interpretation of this divergent instanton-type solution of the Wkv equation. And for that purpose, yeah, we review the construction of instanton-type solution. So instead of using the brute force construction of Torrance series solution, we use the following approach. That is, we first consider some transformation of unknown function like this. Yeah, in fact, we should start with a formal power series solution. And we want to consider it some perturbation. And hence, we change the unknown function from T to W by this formula. So very roughly speaking, this is a localization of the unknown function at this zero parameters formal power series solution. Then the equation becomes to this form for W like this. And to give an analytic meaning to one parameter Torrance series solution, we consider here linearization of this nonlinear equation. That is, we want to eliminate this nonlinear term from this equation in the case of Riccati. And this is really possible. And by considering some transformation of unknown functions of this form, this is again some formal transformation, but by this formal transformation, we can linearize this nonlinear equation equivalent to Riccati equation to this linear equation like this. So we eliminate this quadratic term, and also we eliminate the even part of the coefficient like this. So in this way, in the case of Riccati, we can linearize the equation by a formal transformation of unknown functions like this. And in fact, if such a linearization is achieved, then we can easily construct a one-parameter trans-series solution. In fact, the resulting equation is now a linear equation. We can obtain its solution very easily. That is, a solution of this linear equation is given by this one, just by an exponential function. Then if we substitute this solution of the resulting equation to this transformation, we obtain a solution of the original equation. That is, the solution of the Riccati equation. So this gives one parameter trans-series solution of the Riccati equation. And to give an analytic meaning to the divergent instanton-type solution of Riccati, we consider the following diagram. In fact, we have constructed some linearization of this Riccati equation. That is, we can linearize Riccati equation to this form by some transformation of unknown functions. And besides of the linearization of the original Riccati equation, we consider freezing the coefficient of this Riccati equation. That is, we pick up a special point of x. Then this qx becomes just a constant. Okay, and here we take such a constant to be y here. So this equation is obtained just by freezing the coefficient of the original Riccati equation. And also, this is obtained just by freezing the coefficient. We can also linearize this equation. In this case, linearized equation, the resulting equation has a very simple form like this. And these two linearized equations, both are linear equations, so we can easily transform this equation to this equation by a simple change of independent variable like this. Then by combining these three transformations, we can obtain a transformation from the general Riccati equation to the special nonlinear equation with constant coefficient by freezing the coefficient of the equation. And this is the result. That is, the solution of this nonlinear Riccati equation is obtained by a solution of this equation and the combination of these three transformations. And this equation has with constant coefficient, and we can solve this equation by quadrature. That is, the solution of this equation is given by such an exponential function in a very simple form. And hence, this means that instanton-type solution of the Riccati equation is given by this exponential function substituted some transformation of this form like this. Then in this expression of instanton-type solution of the Riccati equation, any exponential large terms appear, does not appear in the right-hand side. So in this relation, there is no problem of divergence due to the exponential large terms. And hence, in the case of Riccati equations, we find that if the Borel summability of the formal series which appears in the right-hand side of this formula, if the Borel summability of such transformation is verified, then we can give an analytic meaning to the instanton-type solution of Riccati equation. And in fact, the Borel summability of transformation in the case of Riccati equation is in fact verified, is proved by Koike and Shefke. In fact, the right-hand side of this formula is expressed just by the T odd and T even. That is the formal power series solution of the Riccati equation. And hence, its Borel summability is already proved by Koike and Shefke. And if we use the results, we can obtain the Borel summability of the transformation. And hence, as a result, we can obtain the analytic meaning for the instanton-type solution of the Riccati equation. And in fact, if we look at this formula, we can also obtain some information about the singularities of solution of Riccati equation. So this is the result for the Riccati equation. And to discuss the Painlev case, we want to generalize this result to Painlev equations. So this is the final part of my talk. So for example, we consider the simplest Painlev equation, that is the first Painlev equation like this. So to construct a transseries solution or instanton-type solution of this nonlinear equation, we express this equation in the Hamiltonian form like this first. And we consider the localization of the solution around formal power series solution of this Hamiltonian equation like this. This is the localization. Then for the new unknown function u and v, we obtain another Hamiltonian equation like this. And basically, we want to linearize this Hamiltonian equation in the case of Painlev. But it is not possible because, in a sense, Painlev equations are, in a sense, resonant equations. So we cannot linearize this Hamiltonian equation. But instead, we have the work of normal form in the case of Painlev equation. So we cannot linearize the equation, but except for resonant terms, we can eliminate all terms except for such resonant terms. So this means that by some appropriate transformation of unknown functions, we can transform this Hamiltonian system to another Hamiltonian system, where the Hamiltonian function is just a function of the product of two new unknown functions, u tilde and v tilde. So only some resonant terms should remain in this Markov normal form. All other terms are again eliminated. But in a sense, so in this sense, in the case of Painlev, linearization is not possible, but this Markov normal form is enough to discuss the analytic interpretation of instanton-type solution. In fact, this resulting Markov normal form, in this case, in the Markov normal form, the Hamiltonian is just a function of the product u tilde and v tilde. And hence, this Markov normal form should have the form, if we denote the derivative of the new Hamiltonian with respect to this product, the variable product u tilde v tilde, and if we denote this part by k tilde dollar, then the resulting Hamiltonian equation has this form. Okay. So still, this is nonlinear because this coefficient contains the product u tilde and v tilde. But if we multiply the first equation by v tilde, and if we multiply the second equation by u tilde and sum up, then we easily find out the derivative of the product should be equal to 0. And hence, the product should be a constant. That is, this is not this is independent of the independent variable t. And hence, this coefficient becomes just a constant. as a result, we can easily solve this equation just by using an exponential function like this. So hence, in this way, yeah, we obtain a solution expressed described by an exponential function for this Markov normal form. And if we substitute this solution to the this transformation function, we obtain a formal solution of the original Painlev equation. So this is a way of the construction of instanton, another way of construction of instanton-type solution of Painlev. And in fact, and again, then in parallel to the case of Riccati equation, we consider the following diagram. That is, for example, we consider the first Painlev equation. Then by some appropriate transformation of unknown functions, in this case lambda and mu, we can transform it to the Markov normal form like this. So this is again nonlinear equation, but as I explained now before, yeah, the product part is just a constant alpha and beta. And hence, this is essentially the linear equation for the unknown function. And in addition to the first Painlev equation, we consider it another equation, which is obtained by freezing the coefficient. So in the case of P1, if we freeze the coefficient, then, for example, if we assume t equal minus, for example, t equal -6, then we obtain this kind of another nonlinear equation. Then again, for this equation, the Markov normal theory can be applied. And we obtain this kind of another Markov normal form for this nonlinear equation with constant coefficient. And then these two Markov normal forms are essentially the linear equation. And hence, by considering the transformation of independent variable between t tilde and t, we can connect these two normal forms. And hence, combining these three formal transformations, we can obtain a transformation from the first Painlev equations to this another nonlinear equation. And this nonlinear equation is nothing but a nonlinear equation that the Weierstrass wave function should satisfy. And in this way, by this diagram, we can express instanton solution of the first Painlev equation in terms of the Weierstrass wave function like this, substituted this transformation, free formal transformation. And hence, again, yeah, just like the case of Riccati, the right-hand side of this formula does not contain any exponentially large term. And hence, if we can verify the Borel summability of these transformations, then we can give an analytic meaning to formal to the instanton-type solution of the first Painlev equation and the other Painlev equations as well. So this is an analytic interpretation of instanton-type solutions of Painlev. So in fact, the unknown function instanton-type solution of Painlev can be described in terms of the Weierstrass wave function in the case of P1 and such a formal transformation of unknown functions and independent variable like this. And hence, and in fact, this gives, in a sense, Boutrouilla, originally Boutrouilla shows that some asymptotic behavior of Painlev transcendence should be described by an elliptic function near the fixed singularity of the equation. But in a sense, this is the extension of Boutrouilla approximation to all orders. Anyway, yeah. Anyway, by this formula, we can expect analytic instanton-type solution of Painlev can be given an analytic meaning by the Borel summation, just by Borel summation, although it contains exponentially large terms. So this is the final remark. Instead of the conclusion, I would like to give some future problems. And at the present stage, still I have not succeeded in proving the Borel summability. But if the Borel summability of the transformation series which transform the Painlev equation to back of normal form. If the variability of such transformation is verified, then analytic interpretation becomes possible for instanton-type solution. And in fact, if this part is established, then again, we can expect that we can give some analytic interpretation to local equivalence between Pj and P1. So this is related to Nalini's equation first. Yeah. In fact, at the present stage, still instanton-type solution does not have any analytic meaning. But if the variability for such approach is verified, then we can give an analytic meaning. And also, I expect, we can discuss some uniformity, of the transformation, perhaps. But for that purpose, perhaps we have to clarify the relationship between back of normal form theory and the approach of isomorphic deformations. So this is another problem. And also, if such an analytic interpretation of instanton-type solution is established, then perhaps I expect that we can discuss the relationship between elliptic asymptotics due to the Russian people like its Takei, and also with our exact Wkv approach. So this is another problem. And also, if the analytic interpretation of instanton-type solution is established, perhaps we can discuss the relationship of the instanton-type solution between the instanton-type solution and the space of initial conditions of Painlev equations due to Okamoto, Takei, and so on. And finally, we want to generalize such an approach to higher order Painlev equation, but this is a future problem. So still, we have not succeeded in improving the variability, but anyway, if we can prove the variability, then we can give some mathematical rigors, based to our exact Wkv approach, and we can discuss perhaps any connection problem for Painlev equations. Okay, that's all. Thank you very much for your attention.
Hey,
Thank you very much. I wanted to go back to your connection between Stokes direction, Stokes rays for Painlev 1. This is one of my questions, sorry. Just there.
Here or? This is okay.
No, you had some results that go across a Stokes ray.
Okay,
that's the one. Yeah. So perhaps the question you mentioned at the end that you want to relate these results to isomonodromy might answer my question. But there are two very special solutions of Painlev 1, which are completely rotationally symmetric around the origin. They are given by very special initial values at the origin. So what that means is that if you rotate from one sector of angle 2π/5 to another sector, you'll get exactly the same distributions of properties, poles, and so on. So in that setting, I imagine that the relationship across that line wouldn't involve gamma functions. So I wondered how that manifested itself in these connection results.
At present, I have no idea. I cannot understand. But anyway, possibly, if we look at this connection formula very carefully, then we can say something about your question. Possibly. My
other question or comment is really, I don't like beating my own drum, but you mentioned elliptic asymptotics at the end. And I think Martin Kruskal and I were the first to return to Boutroux's results and elliptic asymptotics, and you didn't mention our work at all, so I thought I'd better mention it here.
Okay, thank you. Sorry, I think.
Okay, time for one more quick question before lunch. No?
This type of connection formulas, when you write the normal form, that alpha times beta that are showing up are the same ones as here.
Pardon? Yeah.
When you go to the normal form.
Normal form of what?
So at the end,
Back normal form.
Yeah,
Yeah.
back-
Okay. Yeah.
sorry. Barkov, yeah. That alpha times beta are these.
Yeah.
alpha,
Yeah.
beta.
Yeah.
Okay.
Yeah.
Just wanted to make sure.
Yeah. The same one. Yeah. So yeah.
Okay, so let's thank Yoshi again. And lunch is now down in